Good morning, everyone. Myself, ASHISH VERMA. I'm second year M.Tech IT student, and I'm here with my end sem question paper solution of numerical analysis and design. So let's begin with question number 1. Given a non-linear equation, f of x is equals to x square minus x minus 1 is equals to 0. Apply various numerical methods to find its root, and so on. Solution is bisection method to find the root of f of x is equals to x square minus x minus 1 is equals to 0. Algorithm steps for bisection method. Initial conditions: choose an interval a comma b such that f of a into f of b is less than 0, that is, the function changes sign, ensuring a root exists in the interval. Iterative formula: compute the midpoint c is equals to a plus b by 2. Evaluation: compute f of c. If f of c is equals to 0, where dash is tolerance, then c is the root and stop. If f of a into f of c is less than 0, set b is equals to c. Otherwise, set a is equals to c. Stopping criteria: stop when b minus a of modulus is less than interval small enough, or after a maximum number of iterations. Output: the approximate root is a plus b by 2. First, find an interval where f of x changes sign. Tabular form is given on the screen. Now, geometric interpretation. The bisection method repeatedly halves the interval containing the root. Geometrically plot f of x is equals to x square minus x minus 1, which is a parabola opening upwards with a root between 1 and 2. At each step, compute the midpoint c. If f of c is less than 0, the root is to the right of c. If f of c is greater than 0, the root is to the left. This narrows down the interval, converging to the roots where f of x is equals to 0. Now, error estimation and convergence. Absolute error at each step. Modulus of b minus a is shown in table. Relative error: if the true root is a is equals to 1 plus root of 5 by 2. Relative error at the last step. Convergence behavior: the error of modulus b minus a halves each iteration, so the method has linear convergence with a rate of half. Order of convergence: the bisection method has an order of convergence of 1, which is linear. Now, question number 2. Consider the following data points: 5, 150, 7, 392, and so on. Using Lagrange or Newton interpolation formula of finite differences, estimate the value of function at x is equals to 9. For the chosen interpolation methods, performs the following tasks. Describe the initial assumptions or preconditions. Example: number of data points, form of the interpolation polynomial. Question number B. Compute the value of f of 9 using the polynomial. And question C. Program or algorithm. D. Compare the interpolating polynomial with the actual data points on a graph. E. Question number E. Error estimation, absolute or relative. Solution of the above question. We are to estimate f of 9 using Lagrange interpolation. Assumption and method review. We have 5 data points, which gives us the degree of polynomial equals to 4. Lagrange interpolation formula is f of x is equals to summation of I minus 0 upper limit n, where yi into li of x. Now compute f of 9 using 3 or 4 points. To keep it practical, let's use 4 points closer to x, which is equals to 9. Let's note x naught is equals to 5, y naught is equals to 150, x1 is equals to 7, y1 is equals to 392, x2 is equals to 11, y2 is equals to 1452, x3 is equals to 13, y3 is equals to 2366. We compute J basis polynomials. LO L0, L1, L2, L3. L0 is equals to 1 by 6, L1 is equals to 2 by 3, L2 of 9 is equals to 2 by 3, L3 of 9 is equals to 1 by 6. Now compute f of 9. F of 9 is equals to y0 into L0 of plus y1 into L1 plus y2 into L2 plus y3 into L3, which is 150 into 1 by 6 plus 392 by 2 by 3 plus 1452 by 2 by 3 plus 2366 into 1 by 6, where f of 9 is approximately 860. Now on the given screen you can see the Python program for the given question. Now question number D, the graphical comparison. Plot actual points and the polynomial curves to visually verify accuracy. The polynomial should not pass through all 4 input points and interpolate at x is equals to 9 close to f of which is approximately 860. Error estimation, absolute or relative. Let's say actual value of f of 9 from full polynomial is known to be 855. Absolute error is equals to 5. Relative error is equals to 0.58. Now question number 3. You are given the following set of data points. Describe the intermediate or provide a flowchart for the interpolation based differentiation process. Question number 3b part is present intermediate results and the final value of the derivative. Question number 3 C part, estimate the error in the derivative if possible. Solution for the given question. Given data points are 5 150 7 392 11 1452 13 2 366 17 5 202. We are to estimate first and second derivatives at x is equals to 9 using interpolation based numerical differentiation. Algorithm or flowchart. We will use Newton's divided difference interpolation to first construct the polynomial and then differentiate is to estimate f dash of x and f double dash of x at x is equals to 9. Select 3 or 4 points around x is equals to 9 points Newton. Implement 3-point Newton's interpolation centered around x is equals to 9. Differentiate the polynomial to get f dash x and f double dash x. Substitute x is equals to 9 to get estimates. We choose the closest points to x9, which are 7, 11 and 13. Let h is equals to 2, x0 is equals to 7, x1 is equals to 11, x2 is equals to 13. Step by step numerical differentiation. So you can see the following equation has been derived, in which we get second divided difference which is equals to 32. Now step 2 of interpolating polynomial of quadratic. F of x is equals to 392 plus x minus 7 265 plus x minus 7 into x minus 11 into 32. Now differentiate this. At x is equals to 9 we get f dash of 9 is equals to 265 and the second derivative of f double dash x is equals to 64. Now we get the final results, which is estimated f dash of 9 is equals to 265 and estimated f double dash of 9 is equals to 64. Error estimation. If we had more terms or non-exact derivatives, let true value of f dash of 9 is equals to 268, then absolute error equals to 65 minus 268 is equals to 3. Relative error is approximately 1.1%. But here actual error can't be calculated unless analytical derivative is known. So we state estimated accuracy depends on smoothness and number of points. Now question number 4. Obtain formula for numerical quadrature and obtain Simpson's rule or Weddle's rule from it. Write algorithm for Weddle's rule. We derive Simpson's rule using the Newton-Cotes quadrature formula with 3 equally spaced points where h is equals to b minus a by 2. The points are x0 is equals to a1, x1 is equals to a plus h, where x2 is equals to a plus 2h, which is also equals to b. The function values f0 is equals to f of x naught into f1 is equals to f of x1, comma f2 is equals to f of x2. The general quadrature formula is given on the screen. After integrating, we get the weights where a0 is equals to h by 3, a1 is equals to 4h by 3, and a2 is equals to h by 3. Here the Simpson's rule where h is equals to b minus a by 2. Now the algorithm for Weddle's rule. As you can see, for the following equation, the algorithm can be input function f of x, lower limit a, upper limit b. Step 2, calculate h a is equals to b minus a by 6. Compute x0 x1 up to x6 and corresponding for f of xi. Apply I is equals to 3h of 10, where f0 plus 5 f1 plus f2 plus 6 f3 plus f4 plus 5 f5 plus f6, where the output is equals to I. Example weight keep. When index is 0, weight is 1. When index is 1, the weight is 5. When index is 2, the weight is 1. When index is 3, the weight is 6. When index is 4, the weight is 1. When index is 5, the weight is 5. When index is 6, the weight is 6. Now question number 5, where write algorithm for computation of Gaussian quadrature formula for n is equals to 5 and evaluate pi from integrate of 0 1 dx upon 1 plus x square. The evaluation part, dx by 1 plus x square integral when f of x is equals to 1 upon 1 plus x. This is known to be tan inverse 1 minus tan inverse of 0, which is 5 pi by 4, which is also equals to 0.7854. We will now apply 3-point Gaussian quadrature for n is equals to 3. After applying these three values, we get I is similar to approximately with half of summation of I is equals to 1 with upper limit 3. Now compute values of f1, f2 and f3. Value of f1 is equals to 0.9875. Value of f2 is equals to 0.8. Value of f3 is equals to 0.5595. Where I is equals to 0.7851. Where the final answer is d of dx by 1 plus x square integral is approximate 0.7851, which also approximates the value of pi by 4, in which pi is equals to 3.1404. Apply pivoting and solve the system of linear equation using any direct methods. X plus 2y plus 3z is equals to 14, 3x plus 2y plus z is equals to 10, 2x plus 3y plus 2z is equals to 14. We will solve this using Gauss elimination with partial pivoting. Represent the system as augmented matrix. Apply partial pivoting. Look at the first column 2 4 6. The largest value is 6. Swap row 1 and row 3. Eliminate below pivot column 1. Pivot element is equals to C. Eliminate row is equals to 2. Now eliminate row 3. The updated matrix is on the given page, given PPT slide. Step 4. Partial pivoting on second column. Looks at rows 2 and 3. Second column minus 5 and minus 3 are largest absolute, which is minus 5. So no swap needed. Eliminate entry below pivot in column 2. Pivot is equals to minus 5. Row 3 is equals to row 3 into minus 3 by 5 into row 2. So the new row 3, which is 0 0 minus 19 by 15 comma minus 1 by 3. We will end with it back substitution method, which starts from last equation, which is minus 19 by 15 into z is equals to minus 1 by 3, where z is equals to 5 by 9. Now equation 2 is where minus 5 by minus 7 3 by z, which is gives us minus 5 by, which is at the end gives us y is equals to 4 by 19. Equation 1, 6x plus 18y plus 11z is equals to 7. Give 6x is equals to 7 minus 18y minus 11z is equals to 7 minus 8 into 4 by 19 minus 11 into 5 by 19, which gives us 1 by 9. So the final answer is x is equals to 1 by 19, comma, y is equals to 4 by 19, comma, z is equals to 5 by 19. Now I would like to conclude this PPT with thanking Dr. Shaligram Prajapat sir for giving me this opportunity. Thank you very much.